Cool. Do you remember what we were doing like last time we actually did any learning at all? Born-Haber cycles. Yes, good. Okay. Do you remember specifically what the last thing was that we actually looked at?
Optimization energies and differences between.
Okay. Let's go back to our notes. Let's actually work it all out. Julia, go on.
Factors affecting lattice energy.
Factors affecting lattice energy. Okay. And in particular, hopefully, we looked at polarization of ions. Again, the difference between theoretical lattice energy and experimental lattice energy. Okay. So, can anyone tell me? Come on, let's use our brains for a minute. What would cause a big difference between a theoretical and an experimental lattice energy? Nee.
It won't be a perfect sphere.
Okay, so if the ion is not a perfect sphere, then that's going to cause us a difference, yeah? When might that happen? When might an ion have changed shape? Okay, when it gets polarized. And what would make an ion become polarized?
Differences in charge, sorry.
Go on.
Yeah, fluctuations in charge density, electron density.
Okay, so differences in charge density, I guess, yeah. But what ions are likely to be polarized?
No.
Go on.
Cations?
Cations will be polarized?
No, anions.
Anions will be polarized. Okay, but which anions? Come on, folks, let's actually get some knowledge out here. Maria? Big ones, thank you. Okay, good. Big anions are likely to be polarized. But not just big, something else as well. When they have higher charge, exactly. Okay, so bigger, higher charged anions are more likely to be polarized. Which cations, what kind of cations are likely to polarize them? Small ones? With?
Higher charge. Like
with a higher charge density. Fantastic, there you go. Look, you have knowledge. Look at the knowledge that is coming back to us, yeah? It's stunning. Okay, so what we'll look at today is kind of a little bit of an extension of that, I guess. It's actually the last little bit for enthalpy changes in this topic, okay? We will finish this topic before the summer. We are going to look at enthalpy changes of solution and hydration. So today is, can I even read my watch? Yes, 19th of May. So, have you ever wondered why, hopefully you have, why some ionic compounds will dissolve in water and some ionic compounds just really won't at all?
Oh, I was going to say about some who like solvent, like it depends on the attraction between the solute and the solvent. So
Absolutely, it does depend on the attraction between the solutes, which in this case will be the ions, and the solvent itself, water. Okay? If we know a little bit about these enthalpy changes, we can work out more or less if a substance is going to be soluble or insoluble. Okay? But we need some definitions first. Okay? And some idea of what actually is going on. So, So a little bit of intro there. Here we go. So, when ions dissolve in water, they are attracted to, or they interact with, the water molecules. So I've got a nice sodium ion and a chloride ion. If I just put the sodium ion in water, what will happen to the water molecules?
Like the negative charge on the O is going to to surround the plus charge around the sodium, and then the plus charge on the H is going to surround the chlorine.
Cool. Okay. So you're right. Absolutely. So the oxygen of water will be attracted to the positive sodium ion, okay, because it has the negative dipole, and the other way around, the hydrogens on the water, because they have a positive dipole, will be attracted to the chloride ions. So it might look something like this. Doesn't necessarily matter how many. Going to put in the delta negatives as well. And some delta positives. There we go. And then with the chloride, something like that. Delta positives, delta negatives. There you go. Ugh, horrible looking picture. But what you might actually already have jumped to, I don't know, okay? It's fine to put if I just had the ions on their own in water, or if I had the ions on their own and I put them in water, then that is likely to happen, okay? But if I put an ionic solid in, then first of all I've got to break up the lattice and then have the ions surrounded by water.
Isn't the lattice broken by dissolving it in?
If it dissolves in water, then yes. Okay? But there must be some, well, maybe it's not as obvious as I think. There is some kind of relationship between how strong the lattice is, how much, and then how strong the interaction is between the ions and water. Okay? And we can play around with enthalpy changes, with Hess cycles, to actually see, to work out whether something is soluble or not, okay, or at least to work it out within a reasonable margin, okay. But we need two new definitions of enthalpy changes. So they're going to be enthalpy change of solution and enthalpy change of hydration, okay. And then we're going to write a Hess cycle, and you're going to love it, because I know how you love Hess cycles. For the Hess cycle that I saw in paper 2, the ones that I've marked, they were actually quite good. Impressive. Oh, I shouldn't have said that, should I? Was it a Hess cycle? May have not actually been a Hess cycle. Maybe it was something else. Who knows? Maybe it was in a different universe. An alternative universe is where that happened. Okay. Right. So, yes. Can I take the picture off because I want to do a definition? I don't want to do it that low down. It's a bit rubbish. So I'm just going to take that off. So, definition time. Let's see if I can remember it. So, enthalpy change of solution. So it's the enthalpy change when 1 mole of an ionic solid is dissolved in water to form an infinitely dilute solution under standard conditions. I guess for the most part, when we talk about infinitely dilute, we're talking about it being very dilute, dissolved in a lot of water. Then, next one, I can fit them both on. Enthalpy change of hydration. Delta H hide. So this is what are you confused by? Next definition. Enthalpy change of hydration. So the enthalpy change when 1 mole of a gaseous ion is dissolved in water to form an infinitely dilute solution under standard conditions. Which is quite an interesting definition. What does this remind you of? Gaseous ions. Where? Ionization energy, yeah. But in particular, where did we took gaseous ions and then made something. What's that?
That's right.
James. Lattice energy, exactly, where we take gaseous ions and go to an ionic solid. Here we take gaseous ions and go to a dissolved substance, which is going to be quite interesting for us. In fact, I'm probably already at the point where I can make a Hess cycle. Indeed. So, board rubber. Let's have a think about this. If I go from sodium chloride, solid, to if I go from there to there, what is that enthalpy change from here to here? Bearing in mind all the things we've just defined. So, ionic solid to that. Enthalpy change of solution, absolutely, yeah. Okay. What about if I go from there to there? So from gas to aqueous. That's hydration, okay? Absolutely it is. Just worth bearing in mind that our definition of hydration would be for each separate ion. So this enthalpy change would be the hydration of sodium, but also the hydration of chloride as well. Okay, so they're for separate ions.
Say they've given us a value of what enthalpy of hydration we have to.
You'd have to have an enthalpy change of hydration for sodium and an enthalpy change of hydration for chloride, and they'd be different. Yeah? So that is enthalpy change of hydration. Okay, in fact, put it in there. Both of them together. What can go in the gap here? Huh? Lattice energy, exactly, yeah. Enthalpy, lattice enthalpy or lattice energy, it goes this way, I guess. That is lattice energy. So actually, we can work out any of those, okay, if we know enthalpy changes of hydration, or any unknown in there, we can work it out. Oh, you haven't got the book yet, have you? So, I'm going to have to put it up somewhere. So, you need to be able to draw your own Hess cycle and use the data to calculate the enthalpy change of hydration for chloride ions. So you've got the enthalpy change of solution for MgCl2, lattice energy, MgCl2, and you've got the hydration for Mg2+. Okay? What you're looking for is the enthalpy change of hydration for chlorine, or chloride I should say. Okay? You've just got one unknown. It should be reasonably straightforward. So you're going to have to draw a Hess cycle again, probably similar to what is above there. Okay? And think about what your unknown is. Do bear in mind as well the formula of your compound is important. So I'm just going to change this one around a bit to show what we've got. I think quite a few of you actually got the right answer already, which is great. But we start off with the ionic solids. We go to the dissolved ions. On the bottom we want the gaseous ions. So that's my new Hess cycle for that. Okay. Hopefully you got. If I just take this bit off, I may be able to fit it in the line there. Still see all the numbers. So the way around I did it was to do the enthalpy change of solution equals minus the lattice energy, because I go against the arrow, plus the enthalpy change of hydration for magnesium, plus 2 times the enthalpy change of hydration for chlorides. Okay? I need to take everything else over to that side though, because this is my unknown. So I go, minus 155, minus 2526, so plus Alright, so that number there, what did you get for the number? Huh? Yes. So that's minus 761 is 2 times the enthalpy change of hydration. Why do I keep writing it like that? Therefore, our enthalpy change of hydration equals minus 380.5 kilojoules per mole. Ta-da! That's easy, yeah? One little Hess cycle, that's all we've done in our 45 minutes, and 2 definitions. And before you know it, 45 minutes,